Hi, this is BC Video 7.4b, arc length on the TI and surface area of a solid of revolution. So, there is an arc length option on the TI, and of course I would just press catalog, which is the little book, press the letter A, and then scroll down until you see arc length. It actually tells you what you need, your expression, which would be your function. So if you had y equals x squared, you'd put x squared with respect to x. And then from x equals what to x equals what. Okay? So here's an example. If you wanted the arc length of the function y equals the ln of e to the x plus 1 over e to the x minus 1 with respect to x from ln2 to ln3. If you're in exact mode, you'll get this answer. If you're in approximate mode or you press control equals, you'll get this answer. Alright, so we're moving on to surface area of a solid of revolution. So if you remember when we dealt with area under a curve bounded by two vertical lines in the x-axis, we looked at a little tiny rectangular sliver, and we then added up the areas of all those little slivers. Well, what's happening now is, remember, we're rotating it. So before we were looking at the volume of this thing that we got, and we take the volume of this little disc, because if you rotate this little rectangular strip, you will get a very skinny disc, which is basically a cylinder. But however, this time we're not looking for volume. We're looking for the surface area. So if this was some kind of jug, we're looking for how much paint we'd need to paint the outside of the jug, not the inside. So we're looking for the lateral area of that disc. So if we lay our disc the more traditional way with the bases horizontal and on the ground, the lateral area would be the circumference, which is 2 pi r times the height. So the surface area we're looking for is 2 pi times r times the height. Well, the r, the radius of our little cylindrical disc, is actually the y-coordinate of that point, f of x. The height, of course, is what we would call dx, very skinny, because these are very, very skinny. So there's lots of work leading up to this whole explanation of how this works. I am not going to go through this all with you. I don't even think I have it here. No, I don't. It's just too involved. So what happens is you have y equals f of x. If you want to see it, feel free. If you have a continuous differentiable function on the interval from a to b, then the area S of the surface of revolution formed by revolving that two-dimensional graph about a vertical or horizontal axis is as follows. So the surface area is the 2 pi times the r times the dx. Now, but this is going to be the arc length, so I'm not going to get into where that comes from. Trust me on this one. And there's from your interval from a to b. So the f prime of x dx, and you remember that formula from 7.4a, the arc length is 1 plus the square of the derivative of f of x, and you take the integral of that. So the f of x, you'll just find the derivative of your f of x, square it, and then you'll have this very complicated, in many cases, radicand. But the r of x is the tricky part. The r of x is the distance between the graph and the axis of revolution. So if your equation is given to you as x equals a function of y on an interval from c to d, which would be from y equals c to y equals d, whether you're revolving a horizontal or vertical line, your surface area will be 2 pi integral from c to d of r of y square root of 1 plus g prime of y squared dy, where this r of y is the distance between the graph and the axis of revolution. So here's what's going to happen. You're not really going to decide whether to use x or y based on whether you have a horizontal or vertical axis of revolution, which is exactly what we used to do for volume. We're not doing that this time. You're going to use it in terms of x if the function is given to you in terms of x, and you'll do it in terms of y if the function is given to you in terms of y. So the best way to do this is to look at an example. Now, they're very lame in the book in that I don't know how they expect that you know that this is from 4 to 9. I guess because that's lined up with the 4, I suppose you're supposed to be able to tell that's lined up with the 9. I would certainly tell you. So you have the function y equals 2 root x. Set up and evaluate the definite integral for the area of the surface generated by revolving the curve about the x-axis. Remember, that x-axis has nothing to do with whether we do it in x's or y's. That's going to come into play later. Okay, so here's our formula. We can look at this two-dimensional flat surface that did get rotated. And there is our point on the curve x f of x. So since our y is 2x to the half, our derivative is 1 over root x. That famous distance from any point xy on the curve to the axis of revolution, since the axis of revolution happens to be the x-axis, the distance from any point to the x-axis is going to be the y-coordinate of that point in this case. So we have 2 pi integral from y equals 0 to y equals 9 of our f of x, which of course we have to express in terms of, which is in terms of x, which is 2 root x. The derivative, remember, was 1 over root x, and then comes all the simplifications. So you'll square that, you'll find a common denominator, you'll pull the 2 on the outside. At this point, when you break up the fraction, you'll be able to cancel the root x's, etc., and then you'll evaluate. Okay, here's another function in terms of x revolved about the y-axis. Again, the function, our integral is all going to be in terms of x because our function is in terms of x. And that's from x equals negative 3 to 3. So the derivative of our function is negative 2x. Remember, we will be squaring it, so let's do that right now. So we have, now, the reason it's 4 pi, I could do 2 pi from negative 3 to 3, but I think you'd agree that if I took the region from 0 to 3 and doubled it, I would get the same as 2 pi from negative 3 to 3 because of the symmetry. So that's why I did this, but you could absolutely leave this as 2 pi, and instead of 0 to 3, you could do negative 3 to 3. So the inside is the square root of 1 plus the square of the derivative, which is 4x squared. Now, the distance, this is the tough part, this r of x, the distance between a point on the curve, so pick a point on the curve, call it xy, the distance to the axis of rotation, which in this case is the y-axis, would be the x-coordinate of that point. Now, this happens to be just substitution, let u equal the contents of the radical, the derivative is 8x dx, we've got the x dx, introduce the 8, counteract with an eighth, you're integrating u to the half, u to the 3 halves over 3 halves, etc. Okay, I want to look at number 26, but I want to change the directions. Instead of arc length, I'd like to look at it as find the surface area if you take this region and revolve it about the y-axis, and from y equals 0 to y equals 3. So this is given in terms of y. So, first of all, what does the graph look like if you wanted to graph it? Of course, if I squared both sides, I have what's called a semiconic, and I have the x's are positive, so that would be the right half of the graph. So what happens is the area I'm looking for, they call it S, I call it A. It's a surface area. 2 pi integral from y equals 0 to y equals 3, and here I'm going to have 1 plus the square of dx dy, so I am going to have to find the derivative of this function, so I did that down here, and then don't forget times negative 2y because of the chain rule. So it turns out here's the dx dy and here's the square of it. So I come back up here and replace the square of the dx dy by that quantity. After that, you would find a common denominator, these, etc., etc., etc. Okay?